talk. That's where I did the longest introductions. I didn't understand any of it, but it sounded very kind, so thank you. I'm sorry that this talk, I'm going to break from tradition and give an English talk. I'm sorry for my Spanish or lack of Spanish. So this is going to be a talk about continua. So let me, I know that this audience is a relatively broad audience. I won't assume that you know any of the definitions. I'll give those as we need them. So in particular, when I say a continuum, I mean a compact and connected metric space. And actually, all of the continua in this talk will be subsets of the plane R2, Euclidean plane. So just a compact connected subset of the plane is good enough. So this is a talk about, it's going to be a pretty focused talk about this question, which is due to Mazurkiewicz. This appeared in the second volume of Fundamenta Mathematicae, the journal, topology journal from Poland. They had a tradition of having problem sets in each of those volumes, and the authors of papers were invited to contribute to those sets. And actually a lot of very nice and very important problems appeared there that motivated a lot of topology, especially in continuum theory and also set theoretic topology, for example. So this is one of them. Mazurkiewicz was interested to, well, he and others were interested in characterizations, topological characterizations of some simple and well-known spaces like the arc. So he was asking whether the arc is the only continuum with this remarkable property that it is homeomorphic to every one of its subcontinua, non-degenerate subcontinua. That just means subcontinua containing more than one point. So of course this is a simple property of the arc. When I say arc, I just mean the continuum homeomorphic to the closed interval. And clearly every subcontinuum of this space which has more than one point is again homeomorphic to the whole space. So the question is this a characteristic property of the arc, or are there other spaces like that? And this gives us this definition of what is a hereditarily equivalent continuum. It's one with that property, that X is hereditarily equivalent if it is homeomorphic to every one of its non-degenerate subcontinua. So this is like a very extreme self-similarity property. Okay, it kind of should be reminiscent of like a fractal, except kind of an extreme property like that. Okay, so it turns out that the answer to this question is no, and that was proved by Moïse in 1948. He constructed a new continuum, which he called the pseudo-arc. He called it the pseudo-arc because it has that property in common with the arc, that it is hereditarily equivalent. I will tell you on the next slide what is the pseudo-arc for those of you who have not seen that, so I'll give some details about it. But it turns out that it is another hereditarily equivalent continuum. And there are two other results that I want to mention about hereditarily equivalent continua. So the first one here is due to Henderson, who proved that the arc is the only decomposable hereditarily equivalent continuum. So decomposable, let me give you the definition, just means a continuum is decomposable if it can be expressed as the union of two of its proper subcontinua. Okay, so decomposable continua are like that. You should think of those as sort of common familiar continua. Most common familiar continua, simple ones, are indeed decomposable. In fact, if you have not seen much continuum theory before, you might be hard-pressed to think of an example of a continuum which is not decomposable, which is indecomposable. going to, this won't feature much in this talk, but let me give you one example. The probably easiest or most well-known example of an indecomposable continuum is the so-called canaster bucket handle, which looks like this. Okay, so if you reflect on it for a while, you'll convince yourself that this continuum, which you get by drawing a ray in this pattern, and then taking the closure of that ray, the plane, that is an example of an indecomposable continuum. If you took any subcontinuum of that, which is not the whole space, that will just be an arc, okay, which is nowhere dense, meaning that you cannot express it as a union of just two proper subcontinuum. Okay. Okay, so again, Henderson proved that if you have a decomposable continuum, so a simple continuum, which has this property of being hereditarily equivalent, then it has to be an arc. That's the only one. And Cook, a little bit later, proved that every hereditarily equivalent continuum is tree-like. So again, let me write this definition. X is tree-like. Basically what this means is that if you were to look at this continuum X, X might be relatively complicated or have a complex local structure, but if you look at it from a distance and don't look too closely at it, what you will see is indistinguishable from a tree, just a finite graph with no cycles. So precisely, X is tree-like if for every positive number epsilon, there exists a tree and a function from X to that tree whose point pre-images all have diameters less than epsilon. So in other words, for any arbitrary epsilon, you can squash together points of the continuum X so that you're only squashing together ones very close to each other, and the result will be a tree. Okay, so it turns out that this property of being hereditarily equivalent implies that you must be tree-like. Okay, so our results, and this is what I want to talk about during this talk, is this recent results due to Max Oberstein and myself, that at least in the plane, in R2, the arc and the pseudo-arc are the only hereditarily equivalent continuum. So I'm going to do, for the rest of the talk, two things. First, I just want to tell you some properties, introduce you to the pseudo-arc and tell you some properties about that. And then for the rest of it, I will give some details about how we establish this result here. Okay, so what is the pseudo-arc? So the pseudo-arc is a famous example in continuum theory, very well known. It was discovered actually independently by three different people. Canaster way back in 1922, then Moise and Bing in 1948, and all three of those discoveries were due to for different reasons. They were constructing a space that they did not see at that time was the same space. They were just producing examples of this phenomenon. So here's what this construction looks like. So this is a construction in the plane. I'm going to take just a solid rectangle like that one, and then inside of there, I'm going to embed another topological rectangle, so a disk, but I'm going to put that second one in the first one, inside the first one in a way that is crooked as it goes from, say, this left side over towards the right. It goes almost all the way to the right, but then it goes almost all the way back before finally going all the way forward to the right side. So that's sort of my second approximation to the pseudo-arc. Then inside that one, again, I'm going to embed another disk, topological disk, or you can think of this like a snake, where this one, again, is going to go from the start of the previous one over to the end of it, but along the way, it's going to go back and forth in a crooked fashion. In this picture, I drew it like that, so it sort of zigzags at this level all the way until it gets there. Then we repeat this again inside of that one. Well, the picture gets very difficult to distinguish at this time, but imagine that we put now another snake inside of that one. Again, very crooked as it goes from here to there. This one, if you can make this out from the distance, it starts here and goes almost all the way to the end before it turns around and comes almost all the way back before going forward again in that kind of crooked way. So we construct a sequence of snakes like this, a nested sequence of snakes, and we take the intersection of all of them. And as long as we made sure those paths were crooked enough so that we have this zigzagging phenomena at all scales, large and small, all scales represented, then the result will be homeomorphic to what's called the pseudo-arc. So this is notoriously difficult continuum to draw a picture of because it's got such a complicated structure. And if you try to approximate it, you have such extreme amount of zigzagging that it's impossible to draw a good picture. This is the best that I can do, and it's not very good. Okay, so I'm going to tell you some properties. So first, Canaster constructed this as the first example of what's called a hereditarily indecomposable continuum. So hereditarily indecomposable means that not only is that continuum indecomposable, but all of its subcontinua are also indecomposable. So this was the first example of such a continuum. Moise constructed it again in 1948 and proved that this is actually hereditarily equivalent. So not only is every one of its subcontinua indecomposable, it's actually homeomorphic to the pseudo-arc itself. So for our purposes today, that's the important property, but let me tell you some other ones just for your general information. Bing constructed this in 1948 as an example of a homogeneous continuum in the plane. So homogeneous means that it's totally symmetric in the following sense. If you took any 2 points in that pseudo-arc, then there's a homeomorphism of the pseudo-arc onto itself, taking the first point to the center. So all points are topologically indistinguishable within the pseudo-arc. Okay. Other familiar spaces with this property of being homogeneous are, say, the circle, or in general any connected manifold, topological groups, this kind of thing. Actually, Rodrigo mentioned this, I think, in the introduction, if I understood right, but we were able to prove that, in fact, the pseudo-arc is the only homogeneous continuum in the plane which does not separate the plane into 2 components. And in fact, it follows from that, and a great deal of previous work by other continuum theorists, it follows that the only homogeneous continua in the plane are the circle, the pseudo-arc, this one, and there's a third continuum called the circle of pseudo-arcs, which, just very briefly, this circle of pseudo-arcs is a continuum in the plane that can be mapped with a monotone map onto the circle so that the preimage of each point is a pseudo-arc. Okay, so it turns out, and this is a technical construction, but it turns out that you can take a collection of pseudo-arcs and arrange them in a circle to get a continuum in the plane, which is also homogeneous. Okay, so these are some remarkable properties about the pseudo-arc. And I guess I should point out that this is, at a first glance especially, this is quite a remarkable property. It doesn't look like this would be a homogeneous space, right? For example, you might think that as you complete this construction, you're going to have here, close to this point, there will be what appears to be an end point. And then in the middle, you'll have lots of other points that don't look like that at a first glance. But it turns out that actually every point in the pseudo-arc is an end point in that sense, and you can find a homomorphism between them. Okay, so a few more properties I'm going to list. So the pseudo-arc, this turns out to be the generic continuum. Okay, generic in the sense that if you look at the space of all subcontinua, all the continua contained in the square, let's say. So this is itself a topological space. I'm denoting it as C of the square, so the subcontinua of the square. I'm using the Viator's topology, or equivalently the Hausdorff metric. If you look at the set of all subcontinua of the square, which are homeomorphic to the pseudo-arc, that's a dense G delta. So this is a generic family. So in a colloquial sense, if you picked at random, so to speak, a continuum from the square with topological probability 1 is going to be a pseudo-arc. And the same goes for any n cell, and even for the Hilbert tree. So basically, in the universe of separable energy states. The pseudo-arc is more or less by construction, it's also arc-like. So this was the definition of tree-like. The definition of arc-like is the same, just with the arc, so this space instead of the tree here. So at any level of detail, if you just blur your vision a little bit, when you look at the pseudo-arc, you're going to see something which is indistinguishable from an arc. So for historical reasons, there are two names for that. Same property, changeable and arc-like, but they mean the same thing. And actually being proved in 1951 that the pseudo-arc is the only hereditarily indecomposable and chainable continuum. So this is actually a topological characterization of the pseudo-arc. And it was really this theorem which established that all three of those examples by Knaster, Moise, and Bing were homomorphic to each other. I should mention also that this theorem also tells you immediately why the pseudo-arc is hereditarily equivalent, because any subcontinuum of the pseudo-arc is also hereditarily decomposable and is also chainable, just because the pseudo-arc itself is both. Another property, the pseudo-arc is what we call projectively universal for the class of chainable continua. So not only is it chainable, but it actually maps onto every other chainable continuum. So in that sense, this is kind of like the chainable continuum of maximal complexity. This gives rise to another interesting class of continua. If you look at all continuous images of the pseudo-arc, that includes all the chainable continua, and then many others as well. Those ones are called weakly chainable continua. So I won't really use this definition during the talk, but I do have some questions involving that at the end, so I'll continue. Okay, so that was kind of a crash course introduction to the pseudo-arc. So now let me return to that result about that the arc and the pseudo-arc are the only hereditarily equivalent continuum in the plane, and I'll give you some details about how this proof goes. Okay, so I'm going to start with, this is a notion introduced by Lex Oversteeken and Ed Zimchaten. What's called an epsilon strip in the plane. Okay, so the setup is like this. Suppose that we have two paths in the plane, Okay, I'll trace them with my fingers. So two paths, gamma 1 and gamma 2, which for all time t, they are a distance epsilon from each other. Okay, so imagine them sort of tracing out their image like this. They might back up, but they have to sort of back up together. For all t, they are within epsilon of each other. And let's, for simplicity, assume that they're piecewise linear. That just means the paths consist of finitely many straight line segments. Okay. Then if we take the gamma 1 as sort of the top side, gamma 2 as the bottom, and then join the two ends by straight lines, we get this closed curve like this. And we can look at the regions of the plane which are encapsulated by that curve. So the complementary domains to the curve which have odd winding number. Let me show you a picture or two, for example. So a simple example of an epsilon strip looks something like this. So again, gamma 1 in this picture is this path, which traces out the solid red line on the top. Gamma 2 is the path which traces out that. And you can see if they are parameterized right, they will be within distance epsilon of each other, where epsilon is about that distance. Then we join the ends by straight line segments, and this is in fact a circle in this example. So the epsilon strip is the shaded gray region enclosed by that circle. Slightly more complicated example here where the gamma 1 and gamma 2 self-intersect a little bit. But again, if you look at the way that they move, you can sort of go together so that the distance between the top and the bottom is always within epsilon for all time t. And this gives you a slightly more complicated looking epsilon strip, which has a few regions in the complement. So this big gray one, the curve has winding number 1 there. This white region here is omitted because it has winding number 2 there. And then finally this region, winding number -1. But anyway, this is what we mean by epsilon strip. Okay, so this is kind of the main tool in this study that has something to do with the plane. So let me tell you what. So Overseen and Tipchopton proved, when basically in the same series of papers where they introduced this, they proved that any hereditarily equivalent continuum in the plane can be embedded in the plane so that it is in the nested intersection of a sequence of epsilon strips where epsilon is going down to 0. So precisely, the statement is like this: if you have a hereditarily equivalent continuum X in the plane, then it has a subcontinuum Y such that, so a single subcontinuum Y such that for every epsilon, Y is contained in an epsilon strip. In a sense, this is a funny statement because if X is hereditarily equivalent, that means that this Y is homomorphic to X itself. Okay. So I actually don't know, I didn't really try to prove it, but I don't know if X itself, as embedded in the plane, must it be contained in arbitrarily narrow epsilon strips? Or is it only true of this subcontinuum Y? It's not clear to me. But anyway, this is good enough for what we need. I would like to tell you just a detail or two about how this is, or give you a sense of how this is proved. So let's suppose that X is a hereditarily equivalent continuum in the plane, and let's assume that it's indecomposable, so that it's not an arc. And let's assume that X is drawn on this slide, so that it has at least one point over here, and at least one point over here. And then I'm going to cut with these two vertical lines in between. And since X is indecomposable, actually hereditarily indecomposable, it follows that it has to look very, very crooked as it goes from some point over here to some point over here. It has to go back and forth many, many, many times, so that between those two vertical lines, if you cut by them, you're going to have actually an uncountable family of continua stretching from the left to the right, disjoint continua. And all of those continua are homeomorphic to X itself. Okay. So actually all I need is a convergent sequence of those continua, like that repeater B1, B2, etc., convergent to this one at the top of the infinity. And I have homeomorphisms, those are all homeomorphic to each other, so I have homeomorphisms gi from B infinity to B I, which are getting closer and closer to the identity as I increases. Then if we take a subcontinuum properly contained in here, let that be our y, and now let me show you that this y can be sandwiched between paths in the sense of epsilon strip. So simply I'm going to take, for the top of a strip, I'm going to take a polygonal arc very close to this B infinity, but above it. So hugging the B infinity, but not touching it, as close as I like from above. And then simply, for a large enough I, I'm going to push this C down to get its image, gi of C, very, very close to Bi. And if you take it close enough, then it won't intersect the infinity either, and it will be underneath. And so you get Y contained in this epsilon strip drawn there. So that's kind of the essence of that result. So again, this is very specific to the plane. Because I have a continuum in the plane, I can get sort of a stack of copies of that thing, and that's how you sandwich it between two polygonal paths in the sense of epsilon strip. Okay, so what can we do with that? So two more lemmas I want to share, or results I want to share. The first one looks like this. So suppose that you have an epsilon strip in the plane determined by gamma 1 and gamma 2. So again, here's a picture of that. And suppose that we have a graph in this picture that's this tree consisting of one branch point and 3 legs. Then if you look at the set of pairs of x from the graph and t from the interval 0, 1, the domain of those paths, if you look at the set of all pairs where x belongs to the segment gamma 1 of t, gamma 2 of t, that set will separate g cross 0 from g cross 1. So let me try to explain what this means in a picture. So let's take a copy of this g, and I'll draw it over here. So this symbol triad is homeomorphic to that one. Let's say that this leg corresponds to that one, and then these two correspond to those other two there. I'm going to look at the product of that g with the interval, and now I'm going to take the segment gamma 1t, gamma 2t, and sweep it across as t goes from 0 to 1. And every time that segment, as I sweep across, intersects with the graph g, I'm going to plot the corresponding point in this 3-page book, right, the g cross 0, 1. So I have animated this. Let's see how it looks. So again, I'm just kind of moving this segment as t goes from 0 to 1. I intersect close to the tip of that leg in g, so correspondingly I plot points in that page at that height. And as I keep moving along, I get more and more of those until I get to here where I hit the vertex of that graph. As we move forward from there, now I'm going to have that segment will intersect in 2 places, on this leg and on that one, so I'm going to get points in both of those pages as we go up. Now we arrive at sort of this turning point in the strip, so the segment is going to start proceeding back now, and we get back to the vertex, back into that leg, forward again to the vertex, and then through all the way to the end like that. So this is a semi-accurate picture of what that separator looks like. So now it's hard to read this picture because the lines are kind of on top of each other. Let me just, well, because I worked so hard on that animation, let me run it. So again, we're just sweeping from t equals 0 to t equals 1. Okay, and that is our set described here. And if you look at it, you can see that this separates the bottom g cross 0 from the top g cross 1. You can't get from bottom to top without intersecting that green set. That's the content of this line. And basically what that says is that if you were trying to hide, if you were a particle trying to hide on this graph while that segment sweeps across, well, there's nowhere to hide. You're going to get caught by that segment at some point. Okay, and then here's our theorem, which we proved this in our paper in 2016 about homogeneous continuum in the plane in a slightly more technical formulation. So we get a simpler equivalent statement in this paper, so I'm putting both years there. But this is a general characterization of hereditary indecomposable continua. And this is the, as far as I know, this is the state of the art when it comes to hereditarily indecomposable continua. So let me try to explain this result with some pictures. Okay, so suppose that we've got a hereditarily indecomposable continuum X. Okay, that does not really look like a hereditarily indecomposable continuum, but it's hard to draw that accurately, so let's just use our imagination. Basically, you cannot tell from a single picture of a continuum whether it would be hereditarily indecomposable or not, just because you only have sort of a finite amount of data. So really the only way to tell that a continuum might be hereditarily indecomposable is to get closer and closer, more detailed snapshots of it and see how they look, identify this crookedness in those closer and closer snapshots. Okay, so suppose that we have that hereditarily indecomposable continuum X and a map from it to a graph. In this picture, let's just use G to be this arc, saying like this. And imagine that the function is just the vertical projection down to that point. So the claim is that for any G like that, if we look now in G cross 0, 1, so let me draw that here. So again, this example G is an arc, so that's G cross 0, 1 is nothing but the square. Then it's possible to, and for any open set which separates the bottom from the top here, so let's, for example, take one which looks like this. Then it's possible to find a function h such that the pair GH maps into that separator. So in a sense, it's possible to lift this function g through the first coordinate projection on that separator. What does that look like? Well, again, this view of x doesn't tell the full story. To really see what x looks like, you need to look at closer and closer snapshots. So the claim here is that if you look a little bit closer at x, this is just another picture of x. If x is hereditarily indecomposable, as you look more closely, this crooked structure will be revealed. And indeed, you can ensure that that crooked structure will match with the pattern of this separator here, roughly. So again, this is the same continuum x, but with a more detailed look at it, you find that it actually has this kind of zigzag structure, and that enables you to define the map H such that, or essentially enables you to lift that function G through the separator, through the first coordinate projection on that separator. So according to the theorem, a continuum is hereditarily indecomposable if for any graph and any open set which separates the bottom from the top in this product, you can lift through that separator like this. Okay. For those of you who are familiar with these things, this is a generalization or a strengthening of a characterization of hereditarily indecomposable continua due to Krasnikiewicz and Mies. So their theorem, in a different language, their theorem applies to separators which look just like this one in this example, where G is an arc and U has a simple zigzag shape like that. So this is a stronger characterization where we are allowed to use different graphs and different open sets. So finally, if we put this all together, it together implies the theorem, and let me give you a sense of why that's true. Suppose that we have a hereditarily indecomposable continuum in the plane, which is contained in a epsilon strip like this one. Okay, so we have our x is, again, this picture of x will not look very much like it's hereditarily indecomposable. That can only really be ascertained when we look closer and closer at x. But maybe at a distant glance, this x looks like that. So this is x. So I'm assuming that this x is hereditarily equivalent. And if it's decomposable, it would be homeomorphic to an arc. So let's assume that it is indecomposable. Which means that it is actually hereditarily indecomposable. According to that characterization and theorem of Bing, to prove that this x is homeomorphic to a pseudo-arc, I need to show that it is hereditarily indecomposable, which we have, and also that it is chainable or arc-like. So I need to find a small function from this continuum to an arc, and I'm just going to use the top side of this strip, this gamma 1 here is gamma 2. So to do that, I'm going to, inside the strip, I'm going to approximate x with a graph, even a tree you could choose. So let's say maybe something like this in blue. Okay, so this blue is a graph G, and there's a function from the continuum x to the graph. This is. Let's make this big enough. So you can think of a small function which just pinches together points which are very close to each other with an epsilon or something like that, from x to the graph. So with the property that the distance from x to g of x is small. Okay, according to this lemma here, if we look at the set of pairs like this, so this green set in this picture, that separates the bottom from the top. Let's take a small neighborhood of that. So just fatten that up to an open separator. U, so this U will be a subset of G cross 0, 1, which separates and if a pair X T belongs to U, that means that X is almost on the segment from gamma 1 of T to gamma 2 of T. Okay? So U again is a small neighborhood of this set. So a point in U might not be on that set, but it's very close to it. So it will be very close to the segment from gamma 1 to gamma 2. So now if we, according to this theorem, we can lift that function G through the separator. So basically, if we look at this is the point gamma 1 of h of x. G of x, h of x belongs to this set U. It means that g of x almost belongs to the segments gamma 1 h of x to gamma 2 h of x. So if we then compose these two functions and map x over there to that point, well, that will move x, again, only a small distance. So we have now a small function from our continuum x to the top side of this strip, and that's how we establish that this is chainable and therefore a pseudo arc. Okay, so that was all the detail I intended to give, maybe too much detail for this time of the conference. So let's finish again with a couple of questions. So it still remains an open question whether the arc and the pseudo-arc are the only hereditarily equivalent continua in general. So in the plane, those are the only two, but there could be others which are not planar. According to those results on the first slide, any other example, if there exists any other example, it would have to be hereditarily decomposable and tree-like. And being tree-like implies that it's one-dimensional, so it has to be in R3. It can't be in R2, but it has to be a subset of R3. So that's still open, and in my opinion, very interesting question, central question in continuum theory. So maybe to try to break that up into two more approachable paths, we might try to do it like this. So first, question is, if x is hereditarily equivalent, can we prove that it would have to be at least weakly chainable? So again, must every hereditarily equivalent continuum be an image of the pseudo-arc? This is unknown. And then, just as well, it's not known whether the pseudo-arc is the only hereditarily indecomposable and weakly chainable continuum. So if that is true, that would be a strengthening of this characterization due to being actually quite a strong strengthening of that, and would be very interesting results in itself. Okay, I'll stop there. Thank you very much.